Hi everyone. Today I will be doing a quick little lecture about an important formula in engineering mechanics 2. It is about Lagrange equation. I will explain to you about the formula itself, then I will show few applications of this formula to give a better understanding. First of all, empty your mind, relax, be positive and keep concentrate. Then it will be easy to you to understand. So, this is the basic formula of Lagrangian. Lagrangian equal to kinetic energy minus potential energy. For the kinetic energy, it can be divided into two. First, transition, and the second one is rotational. For the transitions, kinetic energy is equal to half mv squared, or in this course we will be using half mx dot squared. And for the rotational, kinetic energy is equal to half I, which is moment of inertia, time omega squared. And for the potential energy, which is V, equal to mgh, or in this course we will be focused on energy stored in spring, which is half kx squared. So this is the basic formula. Now we move on to the Lagrange equation. Lagrange equation can be expressed as derivative respect to time of partial derivative of Lagrangian respect to velocity, which is q dot, equal to partial derivative of Lagrangian respect to position, just q. So that's it. This is the Lagrange equations. Now let's continue to a simple example. We have a spring connected to a wall and a block connected to the spring, and this is the deflection of x, and this is what we call a system. From the basic formula of Lagrangian, we're gonna find kinetic energy and potential energy. The kinetic energy is equal to half mx dot squared, whereas the potential energy, in this case we're gonna use the potential energy of the spring, which is half kx squared. So this is the Lagrangian formula for this system. Next, we will work on the partial derivative equations. We're gonna calculate these two terms. We start with the derivative of Lagrangian respect to velocity. From this formula, we know that this is the velocity and this is the position. So when we differentiating this respect to velocity, we get mx dot. Whereas when we differentiating this respect to position, we get negative kx. Then substitute these two terms into Lagrange equations. Now we have derivative respect to time of mx dot equal to negative kx. Then solve this one, differentiating velocity respect to time, we get acceleration mx dot equal to negative kx. And this is the final answer. That's it. Now let's continue to another complicated example. For the second example, we have a cylinder on the floor connected by the spring to this wall, then a block on it connected by two springs in parallel on the left hand side and connected by two springs in series on the right hand side. We were asking to find equation of motion by using Lagrange formula. We were given m1 equal to 50 gram, m2 equal to 60 gram, k1 equal to 100 Newton over meter, k2 300 Newton over meter, k3 equal to 3 kilonewton over meter, k4 equal to 150 Newton over meter, k5 equal to 300 Newton over meter, and lastly radius equal to 5 centimeter. As before, we're gonna find the kinetic energy and potential energy. From this system, we have kinetic energy caused by rotational and transition. So kinetic energy equal to half m1 x1 x dot 1 squared plus, because the cylinder rolls without slipping, so it have kinetic energy by transitions half m2 x dot 2 squared plus, and kinetic energy by rotational half moment of inertia time omega squared. So this is the formula of kinetic energy for this system. Secondly, we gonna find the potential energy caused by the springs. So when the springs are connected in parallel, we just add them together. So k1 plus k2 equal to k total. On the other hand, when the springs are connected in series, k3, k4, so we using this formula, k total 1 over k total equal to 1 over k3 equal to plus 1 over k4. Or we can simplify k3 times k4 over k3 plus k4. So the formula of potential energy for this system is equal to half k1 plus k2 plus K3 times K4 over K3 plus K4. So this is the x1 squared plus half kx2 squared. This is K5. So this is the equation of potential energy. X1 for this part and X2 for cylinder part. To simplify the equation of kinetic energy and potential energy, we must find a common point, which is theta. I put as a theta to refer to this part. And so we know that x2 is equal to radius times theta 2, and for the x1, because the block is contact with the cylinder, and the distance from bottom of the cylinder to the bottom of the block is equal to 2r, so we can write x1 equal to 2r times theta 2. So we can convert this into omega, or omega equal to x1 dot over 2r. This is equation 1 and this is equation 2. By comparing these two equations, we get x2 equal to x1 over 2, or in velocity we can write x dot 2 equal to x1 dot over 2. And for the moment of inertia of cylinder, it is equal to half m2 times r squared. So from all this equation, we can substitute into kinetic energy and potential energy equation to make it more easier. So the kinetic energy now is equal to half m1 times x dot 1 squared plus half m2 times x dot 2 squared is equal to x1 dot on 2 squared plus half moment of inertia of the cylinder is equal to half m2 times r2 squared, and the omega is equal to x1 over 2r, x1 dot over 2r and squared. So when we added all this together, we get half times m1 plus m2 3 over 8 times x1 dot squared. So this is the formula of kinetic energy after simplify. Now we look at the potential energy equation. This is the previous equation. To make it easier, we can simplify this long equation into k star, half times k star times x1 squared plus half times k5 times x2 squared. Then we can substitute x2 into x1 over 2. So it's equal to half times k star times x1 squared plus half times k5 times x1 over 2 squared. So the final equation for potential energy is equal to half times bracket k star plus k5 over 4 times x1 squared. So this is the final equation for potential energy after simplified. Now we have kinetic energy and potential energy after we simplify, and this back to the Lagrangian basic formula and Lagrange equations. So now we just substitute these two equations into Lagrangian equation. Lagrangian equal to half m1 plus m2 times 3 over 8 times x1 dot squared minus half times k star plus k5 over 4 times x1. So this is the Lagrangian formula for this system. So next we will work on the partial derivatives equation. So we begin with derivative of Lagrangian respect to velocity. So as we know, this is the velocity and this is the position. So for this one, we just involve the velocity equation. So we get m1 plus 3 over 8 times m2 in bracket times x dot 1. And for the derivation of Lagrangian respect to position, we just involve this one because this is the position. So we get negative open bracket k star plus k5 over 4 close bracket times x1. So as before, we just substitute these two into Lagrange equation. So derivative respect to time of m1 plus 3 over 8 times m2 close bracket times x1 equal to negative open bracket k star plus k5 over 4 close bracket times x1. So solve this one. We differentiating velocity respect to time, we get acceleration, which is x double dot m1 plus 2 m2 is equal to negative so this is the final equation. So to get the answer, we just substitute all the value given into this final equation, then we get 0.0725 times x double dot 1, bring this to left, so plus 6 to 4.2 x1 equal to 0. So this is the final equation we call as equation of motion that we solve by using Lagrange equations. So it is simple and easy, and you just need to keep practice.